Okay, today we're going to talk about the physical properties of ionic compounds and what we've learnt about the structure of these ionic compounds is going to help us understand why they have these properties. Now, if you remember, as an atom takes on an electron, becomes a negative anion. It gains a negative charge, and as it loses an electron, it becomes positive, and tends to form these ionic lattices, where each negative ion is being held in place by up to 6 or 8. If you imagine it's in 3 dimensions, positive ions, and each positive ion is being held in place by a series of 6 or 8 negative ions. Right. So what properties are we going to talk about? We're going to talk about high melting point and boiling point. It's really quite strong structure, but it is brittle, right? We're going to talk about why it's brittle. And then we're going to talk about why it conducts electricity, why it doesn't conduct electricity as a solid, and why it does conduct electricity either as a liquid or dissolved in water. So first of all, let's deal with why it doesn't conduct electricity as a solid. Now, as a solid, it exists as this crystalline structure, much like this. Now, in metals, the electrons can flow freely from atom to atom. This does not, I repeat, this does not happen in ionic compounds. These charges you're seeing here are ions, they're not electrons, right? So all the electrons are still being contained very neatly within each of these ions, right? So there's no electron flow from one side of this compound to the other. Additionally, there's no movement of ions. These ions themselves, the electrons aren't moving, or they're only moving within the ion and within the element, and the ions aren't moving. The ions, this negative here is being held in place by these positives, and this positive is being held in place by this negative. So if you put a battery here and put electrons kind of flowing into here, these electrons would only be able to touch these areas. So the electrons would come in here and wreak havoc with the ionic properties of here, but it's not going to affect the the electron properties of over here, is it? Right? Like these electrons are going to be fine. It's only over here that it's going to be causing any kind of havoc, right? So the electrons will not flow very easily through this process, through um, um, this substance. And the same goes with heat, right? The heat excites the electrons over here, and these start spinning faster. But that doesn't mean that they're going to start moving across the matrix, right? There will be some transference of heat, but it's nowhere near as quick or as efficient as when you have in metallic compounds where it flows through the substance. Um, let's think about the fact that they're solids. Oops, I've just gone too far. Um, they're generally crystalline solids with this repeating arrangement of ions, and they have high melting points because of what's called the coordination number. Before, I was saying that it was 6 or 8. Well, that's considered to be the coordination number, the number of other ions that are holding it in place. This picture, if it was actually completely flat, would have a coordination number of 4. Right? Each cation has 4 4 anions holding it in place. Each cation has 4 anions holding it in place. If we imagine it in 3 dimensions, and there's one in front and one behind, it'd be 1, 2, 3, 4, 5, 6. If we imagined that it was, you could imagine it being differently arranged, such that there are 8. And the more ions holding each other ion in place, the higher the melting point. Brittleness. As we've seen, there's positive and negative ions, right, arranged in this lattice. Well, if we push those ions across, then all of a sudden, instead of being negative and positive aligning, it's positive and positive, and they actually repel. This is really nicely seen when you think about glass. Glass is a crystal. You drop a piece of glass on the ground, it doesn't just fall, it flies apart. You see glass flying across the room. It's because it's not only them just collapsing, the ions themselves are repelling and throwing each other apart because of this repulsive force as the positives line up and the negatives line up. That's why it's brittle. Conducting electricity, means moving charges from one area to another. That's what conducting electricity means. There are no electrons moving other than within the atoms, or within the elements. There's no electron movement from ion to ion to ion once it's in its lattice state. So, in addition, there's no ions moving. So, as a solid, there's nowhere for it to move. However, if you dissolved it in water, or if you melted the salt, then all of a sudden these ions are now free to move in the water. Right, so all of a sudden it is not being stuck. The coordination number is 0. Right, there's no other ions holding it in place. So the cations are free to move to the anion, to the electrode, right, and the negative ions are free to move to the cathode, the anode, right? So that allows for this free flow of electrons, and therefore that's why when we think about ionic compounds, they do not conduct electricity as a solid, but they do conduct electricity when they're put into water or melted. So if you think about salt water conducts electricity, right? But a lump of salt on your desk would not, right? That's all we're going to do today. Answer the question below, and I'll see you in class.